Hi, friends. Welcome again to another episode of Beyond the Clouds, Edge to Edge Transformation. And it's always fun to talk to people who have been in various facets of technology. Dr. Prith Banerjee is somebody I got to know in graduate school. At the time, he was a very well known professor, tenured professor at Urbana-Champaign. But he's done many things and he's left his comfort zone many times. Let's find out why. Prith, tell us a little bit about you.
Hey, thank you, Shankar. It's a real pleasure to talk to you. So, I've had sort of three phases in my career, Shankar. The first phase, first 20 years, I was in academia. First, a professor at the University of Illinois, Urbana-Champaign. Then I was at Northwestern University. I was department head of electrical engineering. And then I was a dean of engineering at University of Illinois at Chicago, doing what professors do. I mean, working with graduate students. I have more than 35 PhD students that have graduated, more than 350 papers, absolutely enjoying the academic part of life. Phase two was, I was involved with two very small EDA, electronic design automation startups. One called ExcelChip that was sold to Xilinx Corporation. Second one, Banerjee, that was sold to Quickstream Media. Both of those startups were based on technologies started in academia, one at Northwestern, the other at University of Illinois. And essentially, I went through the whole process of raising money through VCs, trying to build a product, selling the product, and ultimately selling the companies. And then the third phase in my career, and those two I did while I was in academia. But then third phase in my career was when I left academia, left the deanship at Illinois, and joined Hewlett-Packard as director of HP Labs worldwide. I did that for about 5 years. Then I was CTO at two large industrial companies, ABB and Schneider Electric. And about 5 years ago, joined Ansys as the group CTO. So I have seen innovation in academia. I have seen innovation in startups. I have now seen how innovation gets done in large companies from the viewpoint of a CTO. So I'm having fun.
I can see that. Prith, most people prefer to be in their comfort zone. You were already not only a tenured professor, but a dean at the University of Illinois. And you could have stayed there all your life, and it's very comfortable. What made you go through the exercise of not only starting startups, but then completely leaving academia to do research and now much more practical research?
So that's a great question. And in fact, many of my friends asked that question. And what actually happened was I was in a comfort zone. I was having fun working with my PhD students and doing all the publication and so on. But what I lacked was I found that all the publications I was having, right, was not really having an impact to society, meaning I couldn't pinpoint any products that people were actually using or buying that used the technology that I had worked on, right? And they're all in the publications, and I'm sure somewhere in there was influencing a product, but I couldn't pinpoint a product, which is what motivated me to do my first startup, because I just ended a project called the Match Compiler, sponsored by DARPA. And when I demoed the product to the DARPA program manager, he said, Prith, you're onto something. You should actually convert it. You should transfer the technology to a company. So I talked to the traditional EDA companies, the Xilinx, the Synopsys, Cadence, Mentor Graphics, etc. Right? And it was clear that none of those companies would be in a position to actually build it into a product. If I had to make a product, if a product had to be made, it had to be done by myself. So I just took, that is when I took the jump. I took leave from the university, raised money from VCs, and started the company. And when I sold the company to Xilinx, I came back to academia and I did the second startup. By the time I came back to academia the second time, I felt I had so much fun in the startups. I really enjoyed building products. And that is what motivated me to leave the comfort zone of academia to the corporate world.
Wow, that's exciting. And now I know we are less than a week away from the Design Automation Conference. and you have a very, very interesting topic where you're going to be a keynote speaker. Can you tell us a little bit about that?
Absolutely. So first, let me tell you listeners about what Ansys does. So Ansys is a modeling and simulation company, right? So imagine like an airplane. Before, when an airplane manufacturer builds an airplane, they have a conceptual design of an airplane. They put that design in a CAD model, and they typically in the past used to build a clay model of the airplane wing, put it in a wind tunnel, and do testing of that wing shape in a wind tunnel at say 600 miles per hour to see if that wing actually lifts or not. But that hardware prototyping is very, very expensive. It takes $10 million per wind tunnel test. Or we all drive a car, right? And you have, I'm sure, seen crash testing of cars, right? They'll take a car, run it at 70 miles per hour and bang the car against a wall and see if the dummy inside the car actually survives or not, right? That crash testing is $1 million per crash test. So this is very, very expensive. So what ANSYS does is we take the world around us, which is governed by the laws of physics. It is structural physics, sort of second order partial differential equations called Euler equations, or fluids physics, which is Navier-Stokes equations, or electromagnetic physics, which is Maxwell's equations. And we go back to the fundamental physics and we solve it accurately using numerical methods, using finite element, finite volume, and so on. So this is at the core of what we do at ANSYS, which is around simulation. The trouble with simulation is, yes, it is very accurate, but it takes a long time to run, and it is very hard to do the best setting of these sort of solver parameters. That is where AI machine learning comes in. And so in the last 5 years at ANSYS, I told my CEO that the most exciting opportunity for ANSYS is to marry the technology of AI with the technology of simulation. And so my keynote talk at DAC is precisely that, delivering simulation and design, improving it with AI/ML. And there's some absolutely fascinating work that my team has done at ANSYS. I'm excited to speak to the DAC audience about that work.
Yeah, we won't give out all the secrets until you speak next week. But I have a question. You've been in academics, you've been in startups, and now you're in large companies. Which part of it did you really enjoy the most, or was it like you like everything?
I actually like everything because in academia, what I liked was you are free to pursue any dream, right? Nobody tells you in academia you have tenure. The dean or the department head or the president of the university doesn't tell you, Prith, you have to work on this, right? You literally chart your own destiny, right? Of course, you have to get research funding from the National Science Foundation or DARPA. And I was always successful with funding and so on. So pretty much I could pursue any area. In a startup, the reason a startup is exciting is it's very focused, right? You have one product that you're trying to build, right? And you are insanely focused on that one product. And and of course, there are lots of challenges and so on. And it always, you may have this brilliant business plan that you write, and not always all the things on the assumptions are correct. So you have to pivot. And the pivoting is actually quite the exciting part. Hey, you think you can do this thing, but it didn't work. You pivot and do something else, and you work with customers and learn about new things. It's absolutely phenomenal. But it is one product, right? So it's narrowly focused on that one product. The thing about what I like about large companies is you have 100 startups, right? Essentially, you have so many products, and in each of the products, you're trying to innovate. So you're simultaneously trying to see, hey, what should I do in my fluent product, which is fluid simulation? What should I do in my electromagnetics product, which is HFSS? What should I do in the structural product, which is LS-DYNA, right? And it's sort of exploring the innovation across a broad portfolio of products, and not only doing the incremental changes on this existing product, but thinking about the gaps, right? What new product can I build, right? And should I build it organically or should I do an acquisition? That is actually a very fascinating thing. So all three have its pluses and minuses.
That's amazing. And truly, I can see that in each one of these areas you've excelled. Uh, Speaking of which, We know that 30 years ago, when I got to know you, uh, the United States was doing fantastic, both in engineering, productization, and in manufacturing. Today, we have slipped in manufacturing. This whole CHIPS Act is supposed to help us go beyond and actually regain that market leadership. What's your take on that? How realistic are the goals from the academic perspective, bringing students and academics back into semiconductor manufacturing, from the startup perspective and from the large company perspective?
The world is clearly global, right? I mean, and so in the world of business, right, the business will find the cheapest, most effective way to design the product and manufacture a product and supply the product. So that is the real way. You cannot put some artificial constraint, say, no, you have to only design it in the US and only manufacture it in China and only sell it in India. As soon as you put constraints, it makes the ultimate product non-optimal, right? So the best way to support innovation is to do it without constraints. That is the ideal world. Now we also, in that world, right, that we belonged to 10 years ago, right, the world of in the chip industry, people had figured out that the intellectual sort of newness of new designs and so on, right, there was a lot of very smart people who had landed up in the US, right, from different countries, or maybe from India and China, whatever, but they're working for the most innovative companies, the Intels and AMDs and the NVIDIAs of the world, right? But then in the past, that manufacturing also happened in an Intel foundry or whatever in the US. But then companies like TSMC emerged, right? And Taiwan just basically said, you know what? They're going to really double down on the chip fabrication part, right? And they essentially got not only the equipment, the factories, and the talent, right? So it's not their foundry, oh, it's just manufacturing it in Taiwan. It is the equipment and the knowledge and know-how, right? So Taiwan figured out how to create that entire ecosystem of people, right? When China created manufacturing of large factories and so on, it's not just a single factory, but the whole ecosystem of suppliers and so on. So if you needed some prototype, there was a injection molding person fitted right there who could deliver that right product instantaneously and so on. So as manufacturing moved to China and semiconductor manufacturing moved to Taiwan and so on, that was the optimal way of doing it. You do the design in the US or in Europe and do the manufacturing of it in this, and then you do the assembly somewhere else, right? That is the right way of doing it. Now, basically because of political challenges or supply chain challenges that we found during COVID, right? Oh my God, you cannot get the chip from Taiwan. That's a short-term thing that we found in the automotive industry. And the knee-jerk reaction was, oh, let's just bring manufacturing here in the US. I mean, if you look at the total amount of chip manufacturing in the world, there's so much foundry capacity needed, not for 5 nanometer, 5 nanometer, 3 nanometer, 2 nanometer, 28 nanometer, 100 nanometer for automotive and so on, right? Look at all the technologies and all the factories that $200 billion worth of manufacturing cannot all be moved back to the US and economically. You can put the factories here, but it'll cost a lot more for those factories to build those same chips, right? And the question is, will the customers actually pay for those high costs or not, right? You can say, yes, TSMC, make your factory in Phoenix, right? But when a customer buys, if you are Apple or Broadcom or Qualcomm, and you want sort of 1 million chips from TSMC, they want those chips at, I don't know, $1 per chip, right? They don't care. They cannot say, oh no, I will pay you $2, right, if you make it in America, right? That they will not be, because ultimately their customers will not ask you, right? So this is why it is a very non-optimal thing, right? Now, clearly we have made some progress, right? Certain chip manufacturing has moved here and will be able to do it, but the entire chip manufacturing will never move to the US.
You mentioned simulation, and you mentioned that how simulation is getting with AI is going to be changing the way we simulate. Um, and we keep hearing the term digital twins. How different are digital twins from regular simulators or emulators? And is it what's beyond the hype? What is the reality behind it?
Very good. So let me first talk about the verification problem, right? So you you have a concept of a airplane wing, right? Or a chip and say, hey, this is how, I mean, you know that the wing has to be shaped like this. And if you shape the top of the wing a little longer than the bottom of the wing, that Bernoulli's principle will create the lift. And so therefore the plane will fly, right? That is the fundamental principle. So you create a CAD model of that airplane wing. And then you have two choices. You can actually make a clay model of the airplane wing and test it, verify it through physical measurement and testing, which is very expensive, but it is super accurate because if that plane flies or whatever, you know it will fly. Or you can do that verification through simulation. Simulation is cheaper, right? And you can do thousands of simulations to explore thousands of different sort of wing shapes and so on. But in the past, simulation was not accurate enough, right? So even though you did maybe 1,000 different designs to simulation, the last 100 designs you still actually verified through physical prototyping, right? That is sort of the state of the art today. And that part is called what is called virtual verification and validation. Now, the state of the art has in simulation has moved so much, right? Because of access to the cloud, because of GPU, because of AI/ML and so on, that you can actually do simulation much faster. You can do much larger, more complicated designs and accurate designs than you could do in the past. And so the need for hardware verification is gradually growing away. So increasingly, if you look at 100 designs that needed to be verified, maybe say 30 of the design, originally all 100 were done through physical testing. Then increasingly, maybe 30% of it was done by simulation, and then 70% through hardware. Now it is moving to the point like 70% is being done through simulation, 30% hardware. There will be a point at which we'll go to not 100-0, but maybe 95-5. And that is sort of the direction we are going towards. Now, AI/ML has a role to play here, because as I said, I mean, AI/ML has a potential to greatly accelerate the speed of simulation. And in my DAC keynote on Tuesday, I will actually talk about some methods of what is called top-down methods, bottom-up methods. And I'll show the audience examples of what we have done in different areas of applying AI methods to accelerate simulation. Once that happens, right, and again, this is sort of the power in the future, right? It will greatly accelerate the process of product innovation because people will be able to design like 100 different designs and validate or verify 100 different designs very quickly, mostly through software simulation, and the last maybe 5 or 6 through hardware verification. This is how we'll accelerate product innovation in the next 100 years.
That's amazing. In fact, I attended a conference which you led on digital pharma or digital health. Do you really think that it's going to change the way things seem to be? In other words, in hardware systems, it's mostly physical. But when it comes to healthcare, we worry about biology, life itself. Uh, how, what do you think is the acceptance rate of change in the healthcare space for these kinds of technologies?
That is a great question. And actually, as it turns out, if you look at product innovation in different industries, right? I mean, altogether, the amount of R&D that is invested across all industries is about $1 trillion. Now, and you look at, say, the automotive industry, they have used CAE simulation, right? Computer engineering and design and simulation, right? For the last 30 years. So that area, which spends about $250 billion in R&D, they have a large simulation spend, right? In the aerospace area, right, with all the planes and so on that are being built, rockets, they also use a lot of simulation because those industries have embraced simulation and they've seen the value of simulation and said, you know what, the output of this simulation is as good as the physical prototype. In the healthcare industry, people have not used simulation as much because people are afraid, oh my God, people will die and so on, so they don't trust it as much. So in the area of healthcare, we are still restricted to what is called in vitro trials. So we do we do testing on in pipettes and so on in a lab. Then we do testing on animals. Then we do testing on 1 or 2 humans. Then we do testing on 10 humans, then 1,000 humans, and then ultimately FDA says, yes, this is approved. For example, the COVID vaccine, we all went through it, right? The vaccine was invented in less than a month, and it took 1 year for it to get the FDA approval because that vaccine had to be tested initially on animals, on mice, on donkeys, on whatever, then on 1 or 2 humans, then on 3 humans, 100 humans, 1,000 humans, and then it was approved. And that is the status of clinical trial. That's why it takes so expensive and so on. Enter simulation, right? And we at Ansys are actually working on it, right? So we have, our human body is one of the most sort of complicated things. And inside the human body, the heart is one of the most complicated things in the human body. Turns out that with pure physics, it is possible to actually simulate the human heart, right? Ultimately, because in the human heart, there are these electric signals that come 70 times a minute. In response to the electric signals, your muscles contract. And when your muscles contract, blood flows from the atrium to the ventricle, right? Through the aorta and so on, right? And so that is basically electromagnetics, that is mechanical structures, there's fluids. So if you put it all together in a multi-physics simulation, as we have done at Ansys, right? You could actually model the human heart. And then you say, Prith has arrhythmia, which is irregular heartbeats. You could actually model the irregular heartbeats for Prith. And then you say the treatment is to put a pacemaker. So you can, in a pure lab simulation setup, you could simulate a normal heart function, an irregular heart function, corrected by a pacemaker to make it regular. And you do all that testing and you say, yep, does it work for a male patient? Yes, it does. Does it work for a female patient? Yes, it does. Does it work for an obese patient? Yes, it does. Does it work for a slim patient? Does it work with a patient with blood pressure, with high blood pressure? Does it work with a patient with low blood pressure? Does it work with a patient who is running up a hill? Does it work with a person who is swimming? You could actually simulate all those patient activities and through simulation validate this pacemaker, if you put inside Prith, will actually work. You take these results to the FDA, you can get approval. This is called in silico trials. So instead of using clinical trials, using computer-based simulation trials. And if the accuracy is as good as what people do for car crash testing for automotive industry or for wind tunnel testing in the aerospace industry, this healthcare industry will also transform. It is my belief. And so that is the journey that we are going after in healthcare.
The whole idea of precision medicine, the whole idea of e-clinical trials, I think you folks have come a long way. Do you think precision medicine, which is creating medicines per individual with a digital twin of the human body, do you think it's realistic? Would you see it happening in our lifetime?
Not tomorrow, but absolutely realistic in the long-term future, because here is what we have actually done today. Right? So today, when you do a pacemaker, right? It's a average pacemaker, right? They'll inject this whatever electric pulse every whatever second, right? But imagine I go to a doctor, right? I can take a CT scan of my heart or an MRI of my heart, right? And then I see my irregular heartbeats is this. And for my particular heart, I can have a very specific either medicine like a AstraZeneca drug with 200 milligrams, which will really work for me, or 180 milligrams, which is precision medicine for me, or a precision sort of medicine with a pacemaker. You could actually do that. So what we have done is at Ansys in our CTO office, we are creating patient-specific sort of simulation, right? So we'll go into a doctor, do the CT scan, MRI scan, take those signals, right? Convert it to segmentation, generate the sort of the finite element methods, run LS-DYNA and do the heart simulation and do the post-processing. And as part of our workflow, we can advise a doctor saying that, yep, if you If you do a surgery at this point, you cut the tissue here, this is what the output will be, right? You can do all those what if scenarios and so. Patient-specific surgery is becoming a reality. And similarly, you can do patient-specific medicine, right? You can say this particular medicine, this computational, this chemistry drug, this drug will interact with the cell tissue in this particular way, and it will predict it, and you can actually do precision medicine.
This is indeed fascinating, and it's a dream come true for people who have been looking at all these ideas. Now, if you're a student today, you talked in this short talk, you talked about computational fluid dynamics, talked about semiconductors, you worked in healthcare, you worked in aerodynamics and drones and all that stuff. How on earth can a student figure out where do they want to study? Because everything is siloed. There's electrical engineering, there's pharma, biotech, there's so many little AI. What should a student do? How would you expect them to prepare in all these things?
So I think the knowledge in the world is so vast that it is impossible for a single individual to learn all the content in all fields in detail, not in the time of that 4-year undergraduate, right? So what I think we all have to realize is you go to university to learn how to learn. That's the important thing. Learn how to learn, right? So you are provided a broad overview of, say, CFD, you take mechanical engineering courses or electrical engineering courses, you learn about electromagnetics and so on, right? And then you learn a little bit about AI in computer science, you learn a little bit about programming, right? Once you learn programming in C, then learning to program in Python, etc. is you cannot say I need to learn in C and Fortran and Pascal and whatever, all those languages, right? That is not practical. So in the university, they'll teach you programming and you'll use C as an example of programming. But then in your life, right, you figure out how to learn how to program in future languages. That is how knowledge happens. Same thing, right? You learn about sort of maybe CFD using Navier-Stokes equations and so on, right? You say how this will work for finite volume methods for this, right? And then your problem is actually a structural problem. It's Euler equations. You just adapt. You say, hey, this is what I did for fluids. Now this is how I should do it for structures. Do the necessary just-in-time learning or reading at that time you need to apply it. You cannot learn everything in your 4 years, right? You have to learn how to learn.
I like that concept, just-in-time learning, because we are living in a very dynamic world. And what's your prediction about where the overall industry is going? Because there's that morbid fear that a lot of people have with this kind of automation. We won't need people at a very junior level, whether it's basic QA, basic legal assistants, even basic programmers. Um, how would the future of work look like when all this R&D, which is the very basics, are going to be automated, or it seems to be that way?
Well, I mean, there's been so many times in our life and history, right? People thought, oh my God. So when you and I first came to the US, right, we made a phone call from the US to India, right? 35 years ago, there was an operator who was doing that actual circuit switching. Operator call, make a connection, and that person would make that connection, right? And all of that was completely automated through electronic switching. All of a sudden, 100,000 switchboard operators lost their jobs, right? Oh my God, what is going to happen? Well, they moved into other areas, right? Oh, so here is a little farmer who's doing farming in a 3, maybe 1 acre plot in Punjab, right? And now all of a sudden you have 100 acres, right? Which you can do farming with these John Deere tractors. Oh my God, all farmers will lose their job. Not true. So what has happened repeatedly is sort of the equipment is always going to partner with the human, right? And it's a combination of the equipment or software, right, with the human that will make the human a lot more powerful, a lot more productive. So whatever you could do, right, with your head, you could multiply 2 times 4 equals 8. Yes, you could do that. You could potentially do 2 times 19 equals 38. But if I were to ask you 433 times 9 for 47, in your head, you would be hard pressed to do it. You have a calculator, you type it up, and you get it, right? That makes you a lot more productive. Does it make you useless? No, you're not. You know how to multiply, but you're now using a computer, an equipment to assist you. This is essentially what is going to happen. I think the humans will always be in the core of the creativity. They used a calculator to replace the slide rule or whatever thing that they are using in the past. Similarly, these large language models or whatever will make our jobs easier. So the lower level AI kind of stuff will be done by this AI, and the higher level, more complicated stuff will be done with the human, with the power of the AI.
Prith, you worked in so many different fields, engineering, business, startups. What next? I also know you've done a lot of work in charity and supporting students and all that. Where do you see your career going as you progress along?
So I have also, in addition to doing these things, I have served on boards of a few public companies, Cray and Cubic, and also on a private company called Turntide. So I plan to work on sort of contribute my knowledge to various public and private boards. So that's one of the things I want to do. At some point in the distant future, I will retire from my current job at Ansys. But at that time, I want to give back to society, right? Through consulting, to education, to whatever, right? To mentoring students and more entrepreneurs and so on. So I will keep giving back to society, either on serving on boards, on advisory boards, as mentors and so on.
It's a lot of joy, and we could be talking all day long because you have so many things to talk about. It'll be fun to meet at DAC and talk about all these things. So again, to people who are listening, I'm always looking for interesting people who have done something different in their life and how the whole world is changing around us. And nobody has a crystal ball to answer all these things. No one person can answer all these things. So please come forward and we can have a conversation. So thanks again, Prith. And I
Thank you
look
very
forward
much.
to meeting you at DAC in less than a week.
Thank you very much, Shankar. I had a great conversation. Look forward to seeing you at that. Thank you. Bye-bye.
Thanks.